In this lecture, I am going to present what is portal frame and what is non-sway portal frame and what are the step-by-step procedures followed for the analysis of non-sway portal frame by moment distribution method. Then I would like to solve a problem on non-sway portal frame by moment distribution method. First, coming to what is portal frame. A portal frame consists of a number of members rigidly connected at joints. Such frames, when loaded, deform in such a way that the members meeting at a junction rotate by the same amount and in the same direction. The angle between the rigidly connected members remains the same. So look at this figure. So here this is the portal frame. These are the vertical members and this is the horizontal members. And the members are rigidly connected at the joints. And such frames, when loaded, deform in such a way that the members meeting at a junction rotate by the same amount. This is the frame before loading and this is the frame after loading. After loading, this is the deformed shape of the frame. So here before loading, so what is the angle between the two members, and after loading the angle between the members remain same. So this is the angle between the members before loading and this is the angle between the members after loading. Both the angles are remain same. Due to unsymmetrical loading or due to the lateral loading, the translation of joint takes place. The translation takes place of the same amount. Then what is non-sway portal frame? If the portal frame is symmetric with respect to the loading and geometry, and also if the frame supported at the beam level, then such type of frame is called non-sway frame. Look at this figure. Here the frame is symmetric with respect to the loading, or if the frame is symmetric with respect to the geometry, so that case the sway is prevented, and this is the case of the non-sway frame. Also, if the frame is supported at the beam level, then such type of frame is also called the non-sway frame. So here also the sway prevented. This is the example of the non-sway frame. So analysis of such frames in which the joint translations are prevented follow the same general procedure as for the continuous beam by moment distribution method. If the number of members meeting at a joint is not more than 2, the distribution table similar to the analysis of continuous beams. If the number of members at a joint is more than 2, the same table as used in continuous beams is not convenient. In such cases, slightly different table is used. So then coming to what are the different step-by-step procedures followed for the analysis of non-sway frame by moment distribution method. The first step, assume all ends of the beam are fixed, then find the fixed end moments. Then calculate the relative stiffness of the members and the relative stiffness of the joints. Then calculate distribution factor for all members meeting at a joint. Then balance a joint by distributing the balancing moment to various members meeting at the joint proportional to their distribution factors. Do similar exercise for all the joints. Then carry over half the distributed moment to the far ends of the members. This upsets the balance of the joint. Then repeat steps 4 and 5 till the distributed moments are negligible. Then sum up all the moments at a particular end of the members to get the final moment. These are the steps followed for the analysis of non-sway frame by moment distribution method. Then coming to one example, find end moments of the members of the portal frame as shown in figure using moment distribution method. The relative values of EI are shown along the members. And this is the example of the non-sway portal frame as the support is present at the beam level. And this is the lateral loading present 50 kilonewton at the midpoint of the vertical member AB. On the horizontal member BC, there is present the uniform distributed load of intensity 20 kilonewton by meter. And on the vertical member CD, there is no loading. The horizontal member length is given 6 meter and the height of the vertical member is given 4 meter. And the EI for the vertical member is given 4 and EI for the horizontal member is given 6. So in this question, the frame is prevented from undergoing lateral translation due to support present at C. So this frame can be solved as solve the continuous beam by moment distribution method. So first open the frame A, B, C, D. So this is A, B, C, D. The A support is simply supported and B is the intermediate support and C is the intermediate support and D is the fixed support. So here A is hinge support and B is the joint. So you have to treat it as a intermediate support and C is the joint. You have to treat it as a intermediate support and A is the end support and D is the end support. End support D is fixed and the end support A is simply supported. When you open the frame, the A support become the simply supported and B support become the intermediate support and C support become the intermediate support and D support is the fixed support. So this is the after opening the frame. So this is the shape of the frame A, B, C, D. This is 4 meter AB, BC 6 meter and CD 4 meter. And this is the load is given 50 kilonewton which is present at the midpoint of AB and 20 kilonewton by meter UDL is present on the span BC throughout the length. As you know, the first step you have to find out the fixed end moments. So you have to assume the end of each span is fixed and you have to find out the fixed end moments. First you have to take the AB span and assume the support A and end B is fixed and find out what is the fixed end moments MFAB and MFBA. So MFAB is equal to minus W into L by 8 minus 50 into 4 by 8 is equal to minus 25 kilonewton meter. Similarly, MFBA is equal to plus 50 into 4 by 8. This is equal to plus 25 kilonewton meter. Then take the BC span and assume the end B and C are fixed. Then find out what is the fixed end moments MFBC and MFCB. So MFBC is equal to minus WL square by 12, that is minus 20 into 6 square by 12 is equal to minus 60 kilonewton meter and MFCB is equal to plus 20 into 6 square by 12 is equal to plus 60 kilonewton meter. Then take span CD and on the span CD there is no loading. So the fixed end moment MFCD and MFDC, so both are 0. Then the next step, you have to find out the relative stiffness of the members. As the support A is simply supported for span AB, so you have to find out the relative stiffness of the member KAB is equal to KBA is equal to 3 by 4 I by L. And for span BC, intermediate span, so here the relative stiffness is equal to I by L. And for span CD, at the end D is fixed, so the relative stiffness of the member is equal to I by L. So here you take I is equal to 4 and here I is equal to 6 and here I is equal to 4. So find out the relative stiffness of the members. KB is equal to KBA is equal to 3 by 4 into I by L. 3 by 4 into 4 by 4 is equal to 3 by 4. Then KBC is equal to KCB is equal to I by L. For BC span, I is equal to 6. So 6 by 6 is equal to 1. Here for CD span, KCD is equal to KDC is equal to I by L. But I is given for CD span 4. So 4 by 4 is equal to 1. So this is the relative stiffness of the members. Then find out the relative stiffness of the joints. Support B is one joint and support C is another joint. At support B there are two members meet, that is BA and BC. Find out the relative stiffness of the joint B, that is KB is equal to KBA plus KBC. Similarly, to find out the relative stiffness of the joint C, KC, so you have to take the relative stiffness of the CB members and CD members. So KC is equal to KCB plus KCD. So here the relative stiffness of the joints KB is equal to KBA plus KBC. So you know KBA is equal to 3 by 4 and KBC is equal to 1. 3 by 4 plus 1 is equal to 7 by 4. Similarly, KC is equal to KCB plus KCD is equal to 1 plus 1 is equal to 2. So this is the relative stiffness of the joints. Then find out the distribution factor for the members. As the support A is simply supported, the distribution factor is 1, that is RAB is equal to 1. And due to the fixed end at support D, RDC is equal to 0. Then the distribution factor of all other members find out by taking the relative stiffness of the members divided by the relative stiffness of the joints. So for member BA, so the distribution factor RBA is equal to KBA divided by KB. KBA, this is relative stiffness of the member BA divided by the relative stiffness of the joint B. So this is equal to 3 by 4 divided by 7 by 4 is equal to 3 by 7. Then find out the distribution factor for the member BC. RBC is equal to KBC divided by KB is equal to 1 by 7 by 4 is equal to 4 by 7. Then find out the distribution factor for the member CB. RCB is equal to KCB divided by KC is equal to 1 by 2. Then the distribution factor for the member CD, that is RCD is equal to KCD divided by KC is equal to 1 by 2. So these are the distribution factor for the members. So here balance a joint by distributing balancing moment to various members meeting at the joint proportional to their distribution factor. Then carry over half the distributed moment to the far end of the members. This upsets the balance of the joint. Then the same procedure repeats till getting the distributed moments are negligible amount. Then sum up all the moments at a particular end of the member to get the final moment. This is the line ABCD for support ABCD. First write the distribution factor. So the distribution factor RAB1 write here, and the RBA 3/7 write in this column, and the RBC 4/7 write in this column, and the RCB 1/2 write in this column, and the RCD 1/2 write in this column, and the RDC 0 write in this column. So this is the distribution factor. Then you know the fixed end moments for end of each span. So MFAB, so you write in this column, and MFBA write in this column, MFBC write in this column, then MFCB write in this column, then MFCD write in this column, then MFDC write in this column. So here you know the fixed end moment MFAB is equal to minus 25, and MFBA is equal to plus 25, and MFBC is equal to minus 60, and MFCB is equal to plus 60. So this is the fixed end moments. As the end A is simply supported, so first you take the balance of simply supported end A, then take the carryover of this moment. So here, so this is the fixed end moment. So this moment you have to balance by multiplying with the distribution factor, and you have to put in opposite sign. So here the moment is given minus 25 into 1, and that you have to put, that you have to balance by opposite sign, plus 25. You know, at the simply supported end, the moment is 0. So here after balancing of joint A, here you got the total moment is here equal to 0. Minus 25 plus 25, this is equal to 0. The simply supported end A is already balanced. Then carryover of this moment to the other end of the same members. So here you take the carryover of the half of the moment to the other end of the members. Here carryover 12.5. Then draw one line here, then take the total moment. So here minus 25 plus 25, this is 0. Write here the moment for distribution, and here minus 25 plus 25, this is 0, and here plus 25 plus 12.5, so this is 37.5, and this is minus 60, here you write minus 60, this is plus 60, and here there is no moment, so here the moment is 0. So this is the moment for distribution. Then distribute or balance the moment at the other joints, that is at B, C and D. So here you know the moment for distribution, and distribute the unbalanced moment at joint B and at joint C. So at joint B, the unbalanced moment, that is 37.5 minus 60, and this moment you have to balance by multiplying with the distribution factor. So the unbalanced moment, that is 37.5 minus 60 into 3/7, that you have to put here in opposite sign. Similarly, what is the unbalanced moment, that you have to multiply with the distribution factor 4/7, and you have to put here in opposite sign. So this is the balanced moment 9.64, and here the balanced moment, this is 12.86. Then go to the joint C. So here the unbalanced moment, this side 60 and this side 0. So the unbalanced moment is 60, and this unbalanced moment you have to balance by multiplying with the distribution factor 60 into half, and you have to put in opposite side minus 30. Similarly 60 into half, and you have to put in opposite sign, this is minus 30. So this is the balance of joint B and C, and here there is no moment, and this is 0 distribution factor, so here this is your 0. So this is the balance or distribution of the joint B and C. Then again you go for the carryover of the moment. At the support A is balanced, here the carryover of this moment not takes place to this end, and here this moment, the half of this moment will carry over to this side, and half of the moment will carry over to this side, and here the half of the moment will carry over to this side. So this is the carryover of the moment. Then again you go for the balance of joint B and C, or distribution of joint B and C. So at joint B, the net moment or unbalanced moment, that is minus 15. This side 0, this side minus 15. And this moment you have to balance by multiplying with the distribution factor. So minus 15 into 3 by 7. So you have to put here in opposite sign, plus 6.43. And this is minus 15 into 4 by 7. You have to put here in opposite sign, plus 8.57. So what is the unbalanced moment at joint B? So that moment is balanced by multiplying with the distribution factor. So minus 15 into 3 by 7 is equal to plus 6.43. Minus 15 into 4 by 7, that you have to balance, that is equal to plus 8.57. Then take the joint C, and what is the unbalanced moment at joint C, and that moment is balanced by multiplying with the distribution factor. 6.43 into half, this is you have to put in opposite sign, minus 3.22, and 6.43 into half, this is equal to minus 3.21. Then here the moment minus 15 into 0 is equal to 0. So this is the distribution or balancing of the joint. Then again you go for the carryover of the moment. So here the half of the moment will carry over to this side, and half of the moment will carry over to this side, and half of the moment will carry over to this side. So this is the carryover moment. Then again you go for the balancing or distribution of the joints B, C, D. So here this is the unbalanced moment, and this moment you have to distribute or balance by multiplying with the distribution factor. So minus 1.61 into 3 by 7, and you have to put in opposite sign, this is plus 0.69. Similarly minus 1.61 into 4 by 7, and you have to put in opposite sign, that is plus 0.92. Similarly at joint C, so this is the unbalanced moment, and this moment you have to balance or distribute to both sides by multiplying with the distribution factor. So 4.29 into half, this is equal to minus 2.15, and 4.29 into half, this is equal to minus 2.14, and here minus 1.61 into 0 is equal to 0. So this is the distribution or balancing of the joint. Then again you go for the carryover of the moment. So half of this moment will carry over to this side, half of this moment will carry over to this side, and half of this moment will carry over to this side. Then again you go for the balancing or distribution of the moment at joint B, C, D. What is the net moment at joint B? That is minus 1.08, and that moment you have to balance or distribute to both sides by multiplying with the distribution factor. So minus 1.08 into 3 by 7, so you have to put in opposite sign, plus 0.46, minus 1.08 into 4 by 7, and you have to balance by opposite sign, plus 0.62. Similarly the unbalanced moment at the joint C, that is 0.46, and this moment you have to distribute to both sides by multiplying with the distribution factor. So 0.46 into half, this is equal to minus 0.23, and 0.46 into half is equal to minus 0.23, and here minus 1.07 into 0 is equal to 0. So this is the balancing the moment at the joint B, C and D. Then again you go for the carryover of the moment. So half of this moment will carry over to this side, half of this moment will carry over to this side, and half of this moment will carry over to this side. This is the carryover. Then again you go for the balancing the moment at joint B, C, D. So here the unbalanced moment at joint B minus 0.12, balance the moment by multiplying with the distribution factor and put this side the moment is 0.05, and minus 0.12 into 4 by 7, and you have to put in opposite sign this side plus 0.07, and at the joint C the unbalanced moment 0.31, and multiply this moment with this distribution factor and put here in opposite sign minus 0.16 and 0.31 into half and put in opposite sign, that is minus 0.15, and here this is the unbalanced moment at joint D. This into 0 is equal to 0. So here you got the moment of negligible amount, that is here you got 0.05, 0.07, minus 0.16, minus 0.15, negligible amount, that is to the decimal point. So sum of all the moments at a particular end of the member to get the final moment. Here this end the moment is already 0, you got 0, and take the moment, this is the moment for distribution, and take the sum of all the moment here, and this moment is equal to 54.77. Similarly the sum of all the moments here, this is equal to minus 54.77, and here the sum of all the moment is equal to 35.73, and here the sum of all the moment is equal to minus 35.73, and here the sum of the moment is equal to minus 17.80. So these are the final moment. Then you can check at the joint the sum of the moment should be 0. So here you see at joint B the sum of the moment MBA plus MBC, that should be 0, 54.77, and this side minus 54.77. So the sum of the moment at joint B is equal to 0. Similarly check at a joint C the sum of the moment coming 0 or not. Here MCB plus MCD should be 0. MCB is equal to 35.73 and MCD is equal to minus 35.73, so the sum is equal to 0, and MDC is equal to minus 17.80. So here the final moment MAB is equal to 0, and MBA is equal to 54.77, MBC is equal to minus 54.77, MCB is equal to 35.73, and MCD is equal to minus 35.73, and MDC is equal to minus 17.80. So this is the direction of the moment. So here MAB is equal to 0, MBA is equal to 54.77 kilonewton meter, MBC is equal to minus 54.77 kilonewton meter, MCB is equal to 35.73 kilonewton meter, MCD is equal to minus 35.73 kilonewton meter, MDC is equal to minus 17.80 kilonewton meter. So give the direction of the moment. Here there is no moment, and MBA is equal to 54.77 positive, so give the direction clockwise. MBC minus 54.77, so here this is anti-clockwise, and MCB 35.73, clockwise, and MCD minus 35.73 anti-clockwise, and MDC minus 17.80 anti-clockwise. These are the direction of the movements. Then you can draw the final bending moment diagram. So here there is no moment, but here this side the moment MBA is equal to 54.77. So here you take 54.77 and here no moment, so join this one. So this is the negative bending moment diagram for this member, and here this side the MBC minus 54.77 and the MCB 35.73. So here you take 54.77 and 35.73 and draw these 2 points, and this is the negative bending moment diagram. Similarly, MCD, this side you take 35.73 and this side take 17.80 and join these 2 points, 35.73 and 17.80, and join these 2 points, and this is the negative, and this side the tension in inner side that you take positive, plus, and this is minus, and this total minus, and this is minus. Then you know what is the load is present on the frame. The load is present 50 kilonewton at the midpoint. So the free bending moment or positive bending moment diagram is triangular. So that is WL by 4. So W is given 50 and L is equal to 4. So 50 into 4 by 4, that is equal to 50 kilonewton meter. Similarly, on the horizontal member BC, there is present the uniform distributed load throughout the span, that is 20 kilonewton by meter. So the free bending moment or the positive bending moment, that is parabolic, that is equal to WL square by 8, 20 into 6 square by 8. So this is equal to 90 kilonewton meter. So this is parabolic, and here the positive bending moment diagram is triangular, and here the positive bending moment diagram is parabolic. So here this, the overlapping negative and positive, this is cancel each other, and here also the negative and positive, the overlapping portion cancel, and this is the net bending moment diagram. So here this is positive, this is negative, this is negative, this is positive, this is negative, negative, positive. So this is the final bending moment diagram. Then you can find out what is the maximum positive moment here and what is the positive moment here. So as you know, in the slope deflection method, by taking the similar triangle here, two triangle, and you have to find out what is the ordinate here, then you have to find out this ordinate, then from the total this ordinate you have to deduct this ordinate, and you can find out what is the positive moment here. Similarly, here you know this ordinate, and here also you have to find out this ordinate by taking two similar triangle. After knowing this ordinate, so from this total ordinate you have to deduct this portion, so that you will get what is the positive moment here. So this is the complete final bending moment diagram of the non-sway portal frame. Now all are clear how to solve the non-sway portal frame by moment distribution method.